Here in example 4 from chapter 5, we have, I think, a pretty interesting example of having a printhead where you're trying to, let's say, make an image here over a piece of paper being held against a fixed surface here through some activation force F of t, and we'll idealize that activation force as being some step there in time. So we know what force it takes to make the correct impression, but two things we have to watch out for. One is that we cannot have too much overshoot. As when you apply this force F, there may be some obstacles, some part of the other print mechanism here, which is going to cause interference with the print head. So you want to make sure that the overshoot here is not too large, and you don't want to slow down the printing process. You want that to do in such a way that the settling time is small. So we're going to say that for a mass head here at 0.02 kilograms, we don't want more than 9% overshoot here because of the other interferences, and we want to have this process occur in something less than 1/10 of a second. So as we go through the derivation of the equation of motion, FBD, Newton's second law, is going to give us an equation of motion that looks like this. If we put this in its standard form, we divide through by m, making the coefficient in front of y double dot a 1. So this is y double dot plus c over m y dot plus k over my is equal to the applied force there divided by m. And their standard form of the equation says that this is what our natural frequency squared is. And this number here is defined as 2 times the damping ratio of zeta times omega n. Now what we learned from a lecture is that 1, the percent overshoot for an underdamped system like this, that is 100, that's converting it to percent, E minus pi zeta divided by the square root of 1 minus zeta squared, like this. So if we put in our design criteria here of 9% overshoot, basically says that we cancel this out, make this a 0.009. If we take the log of both sides, we get minus zeta divided by the square root of 1 minus zeta squared is equal to the natural log of 0.09 as that. So if I square both sides, I get pi squared zeta squared divided by 1 minus zeta squared is the log of 0.09, that quantity squared. And therefore I can solve for a zeta from here as being the square root of the log of 0.09 squared divided by pi squared plus log of 0.09 squared with the square root as that. So in order to meet the criteria for the percent overshoot, all we need to worry about is the damping ratio. So we have to have a damping ratio of at least 0.608. The other criteria has to do with the settling time, T sub s. And we saw that for the 2% settling time, we need Ts to be equal to 4 times the time constant. The time constant for the underdamped second order system here is zeta omega n as that. So from this we can see that the natural frequency of our printhead system, which from here we get is 4 divided by zeta T sub s, So that's 4 divided by our number we found for the damping ratio, which is 0.608. And the settling time here of 0.1 says that our natural frequency right there on the boundary between acceptable and not acceptable is 65.8 radians per second. So these are parameters that come about from our mathematical model. We now need to relate those back to the physical ones. From our equation of motion, omega n, the undamped natural frequency is the square root of k over m. So from this we can see that the value of k that we need to meet that criteria is m times omega n squared. They gave us the printhead mass of being 0.02, 65.8 squared, like that. So the printhead stiffness then must be, to meet our criteria here, is 86.5 newtons per meter. Also from our normalized standard form differential equation, the 2 zeta omega n was c over m. So from this we see that c is equal to 2 m zeta omega n. So that's 2, the mass we know was 0.02. For our overshoot, we saw we needed a damping ratio of 0.608. And from our settling time, we found that the natural frequency that we need here is 65.8. So that is 1.60 newtons second per meter. So these are the physical values for damping coefficient C and the stiffness of that printhead in order to meet that criteria. So these results that we used here, the equations for settling time and percent overshoot, you might recall were based on understanding where the poles were in our complex plane. So let's make a sketch of what we had there. So let me draw out the complex plane here, real and imaginary parts. So this axis here was the real part of our pole, the imaginary part on this axis as that. So recall that the settling time was directly related to the damping ratio in omega n as this. One thing that we saw from looking at our poles is that lines of constant zeta omega n were like this. Why is that? Well, because the real parts of our poles were minus zeta omega n. So any line here that's parallel to the imaginary axis corresponds to a constant value of that. The important thing is that since this is equal to 4 over TS, it says that settling time is also a constant on this line. The second thing that we saw was that the percent overshoot for the underdamped case was 100. Again, the 100 there was to convert to percent times the exponential of the exponential minus pi zeta divided by square root of 1 minus as zeta squared as that. So lines that we saw in from a lecture of constants as zeta were radial lines coming from the origin. So this radial line here corresponds to damping ratio equal to a constant. And therefore, based on our equation right here, we see that this also means that the percent overshoot is also a constant under that definition. So if we want the damping ratio to be sufficiently large that we keep our percent overshoot down, we need to be on this side of these lines. And if we want the settling time to be small, we want zeta omega n in magnitude to be large, so we need to be on the left side of that. What this says is that where we want to be with our design is somewhere along here. Okay, I think the number that we had ends up being right there, but anything over in this region here will satisfy our criteria, because we're trying to make the percent overshoot as small as we can and the settling time as small as we can. So the numbers we had were there, but anything over there in the red hashed region there corresponds to something that will satisfy the design criteria on settling time and percent overshoot.